Hi, everyone. My name is Chen from Nanyang Technological University. Before the presentation, I have to mention that all the authors of this work cannot come here due to the US visa issues. So therefore, I'm glad to be here to help them present offline. So if you have, like mentioned by the session chair, if you have any questions, please post it on the Slack channel, and the leading author Wang Junjie will handle it online. So this work is named FuzzJIT, the Oracle Enhanced Fuzzing Technique for JavaScript Engine JIT compiler. The authors are from Tianjin University, Tianjin Group Corporation, and Monash University. We all know that browsers are playing an important role in our daily life. For example, when the author wrote this paper, all the authors collaborated with each other using the online LaTeX writing system such as Overleaf. When we registered for the USENIX security event, we used the online banking function of the browser. Therefore, the safety of the browser are critically important to our property and our privacy. However, the browsers can get compromised sometimes. For example, at the Pontoon 2022, the Manfrey poll successfully breaks through both Firefox and Safari browsers. Through the investigation, we find that in most cases, the vulnerability gets exploited is inside the JS engine of the browser, and the JS engine parses, executes, and optimizes the JavaScript source code within the web page. Here is a general architecture of the JS engine, which contains 4 key components. Firstly, the JavaScript source code will be parsed by the first component parser as the abstract syntax tree, aka the AST, and the AST will be converted to the bytecode using the bytecode generator. And thirdly, the component interpreter can execute the bytecode. However, if the given bytecode is repeatedly executed, reach a threshold number of iterations, it will be labeled as a hot part, and the JIT compiler, the 4th component, will be triggered to compile the bytecode into assembly code and optimize its code logic. Indeed, the JIT compiler did a lot of the optimizations, like dozens of the optimizations, including the bound check elimination, data code elimination, etc. As shown in the left part of the slide, you can see the example code first assigns the variable c as the result of the plus of a and b, and they did the code did the same thing to initialize the variable d. However, if these pieces of code snippet be optimized by the JIT compiler, the assignment of the variable d will directly be the result of the c instead of computing them again. However, the JIT compiler, the optimization thing is very challenging and error-prone. It is mainly because JavaScript is a weakly and dynamically typed language. For example, in the left side, the variable a can be assigned first by an integer, then by a string, and then by an object like the dict array, etc. This is not allowed in some strong typed languages such as C, C++, or Java. But it is very common in the JavaScript. So at many times, the JavaScript, the JIT compiler does not know the type of the variables inside the target code it needs to optimize. So most JIT compilers, they follow a general process that first profiling the variable types with the runtime information such as the previous execution results, and then they make the optimization decisions. So here is an investigation of the existing JIT compiler bugs. In recent years, the JIT compiler bugs are the main attack surface of the browsers. And we can see in the figure, the number of the JIT compiler bugs is around 4 times that of the parser or interpreter bugs during the past 4 years. Among the 8 successful point-to-earn demonstrations from 2019 to 2021, 6 of them have exploited 5 different JIT bugs. So in this work, the authors set the goal as proposing some advanced fuzzing techniques to detect more JIT compiler bugs. So throughout the investigation, we found that the existing JavaScript engine fuzzing works mainly using crash as the only oracle to detect the JIT bugs. So this raises a question, is using the crash as the only oracle enough to detect these bugs? Well, to answer this question, they dive into a particular bug in Chrome V8. This bug is a typing error related to the API, to the math.expm1. So this API basically, it accepts a parameter x, and it first calculates the exponent of the x, and then -1. So if, in this case, if you give x as -0, it will return -0. So we can see a POC example of this bug as shown in the left side. There is a function called foo, and the foo returns the result of the object.is. Object.is is used to determine whether two values are the same thing. So as we said before, the math.expm1 with the input parameter -0 will return -0. So if before the optimization, these pieces of the code snippet, it will return true because they are basically the same thing as the -0. However, if during the optimization, this part, the function call part of the math.expm1, it will be replaced as 0. So 0 here is not exactly the same as the -0. So the result is that the return value of the function foo is false. So to this stage, your audiences may question that what harm can such a subtle differences do? Well, the reviewers of this bug also concerned about this at the beginning. However, someone proves that this is exploitable in certain cases. So if anyone is interested in this exploitation detail, you can refer to the related technical report. And we also found that there exist many other such kind of JIT bugs. They have certain characteristics that they can only cause subtle differences before and after optimization rather than the crash, and they are possibly exploitable. So from this motivating example, they also build the basic insight that JIT compiler should only speed up the execution speed of the code, but should never change the output of the code. So this is the basic insight. Based on this, they proposed an enhanced oracle to detect both crash and non-crash JIT bugs. Well, the proposed approach has 3 key components. First, we should guarantee that every generated test case can trigger the JIT compiler. This means that we are testing the target code we want to test. Secondly, when a discrepancy occurs, we should be able to recognize it and capture it. And thirdly, the mutation strategy should be able to reveal the JIT compiler bugs, reveal more JIT bugs. Well, for the first step, from the specification, we can know that the JIT compiler can be triggered automatically when certain JS code be repeatedly executed, when it becomes hot. So to do that, we wrap the testing content, the generated JavaScript source code, into a function called opt and invoke it repeatedly inside a for loop. So you can see the example. In the example, we set the iteration number as 1,000. However, for specific JavaScript engine, the threshold number should be different, and we manually investigate it and set it accordingly during the real-world testing. And for the second step, capturing the discrepancy, to capture the discrepancy before and after the optimization, we can compare if the return value of the function before and after optimization deeply equals. So this is basically something like this. The first parameter before JIT records the return value of the opt function, and after JIT records the return value of the function after the optimization. If they are not deeply equals with each other, it may be a JIT bug, so we raise the crash to capture it. Well, to eliminate the possible false alarms, the tester could we forbid the generation of some APIs like the math.random, the date.now, etc. Well, thirdly, for the mutation strategies, to reveal more JIT bugs, we increase the probability of the generation of some JIT bug-related elements, such as arrays, objects, and interesting numbers. These contents are enclosed in the testing function. For the implementation, the approach is basically a combination of FuzzJIT and one template. The FuzzJIT is a coverage-guided fuzzer for JavaScript engines based on a custom intermediate language fuzzer IL. To this work, FuzzJIT provides the coverage guidance, the fuzzing queue, organization, the test case execution, the fault detection, etc. Finally, they evaluated the FuzzJIT, and for around 1 month, they found various new bugs, like 10 bugs in the JavaScriptCore, 5 bugs in the Chrome V8, 2 bugs in the SpiderMonkey, and 16 bugs in the ChakraCore. All these bugs are inside the JIT compiler code part. Well, they also compared the coverage, found that the FuzzJIT outperforms the SOTA fuzzers in the coverage metric. So this is basically all of the presentation, and thank you for your attention. If you have any question, please reach out to the leading author via Slack or email. The leading author is called Wang Junjie. Thank you.